In this video, we are going to find asymptotes of a function, both vertically and horizontally, using our graphing calculator to help us. So, in this problem, we have to remember, how do you find asymptotes just in vertical asymptotes just in general? Well, that's when your denominator is equal to 0. So similarly to our method that we use for x-intercepts, instead of worrying about the entire function, I'm going to worry about just setting the denominator, getting the denominator in my y1 line. But just before we do that real fast, you can see by looking at the graph, you can see it looks like we do have a vertical asymptote somewhere right in here. Oh, in my window, if you want to mirror it, I'm just going -2 to +2, -10 to +10. So you can see it looks like we have a vertical asymptote right in here. So it looks like it's somewhere between -1 and +1. And if we back out a little bit, if we make to just kind of verify, let's look from -10 to +10. You'll see it looks like that's our only asymptote, unless maybe one is being hidden somewhere right on the axes, because we can do that to you, is sneak a vertical asymptote on the axes. So here's how we do this. Well, we use the concept of the vertical asymptote is created by the denominator equaling 0. So therefore, I'm going to take my denominator and get rid of the whole function. I don't care about all the rest of it. Actually, well, it's too late now. So we're going to go ahead and put that in, and we're going to put in just the denominator. There we go. So now when I go to look at this graph, all I care about is where I have a 0. And you'll notice we know this is a cubic function, and it's opening up, so if we were to see any zigzags, we would be seeing them by now. So it looks like all the interesting parts of the graph, any maxes or mins, would have happened already. So similarly to how we found an x-intercept, where we wanted the numerator equal to 0, we do the same thing here. And we can go ahead and set our window going from -2 to +2 if you would like, just to kind of narrow down what we're seeing. And then also just to really focus in on intercepts so things don't get hidden. I always like to go ahead and make the y values very narrow, so it should jump out at us where there's an intercept. So, and you see it popped in right there. There's where our intercept occurred. That's where our 0 is. So when I go second, calculate, again I want a 0. And now you'll notice my cursor starting off at x equaling 0 with a y value of 1. So, and it wants a left bound. So the left side of my graph would be where it's negative. So notice I've moved my cursor to the left. I'm now in the negatives, and my y values are now negative. So I hit enter. You'll see our little arrow just popped up, and it's showing it's on the left side. Now, as I move my graph to the right, notice my y values just popped to the positives. So I'm going to go ahead and hit enter. And you see we have a 0 at -0.2640011. So therefore, I know I'm going to have a vertical asymptote. I'm going to have a vertical asymptote at x is approximately, that's the world's worst approximately, let's try that again, approximately -0.2640011. So again, we're not going to get the exact value, but this gets us a good idea of where a very, very close idea to where our vertical asymptote is, and good enough for what we're doing since we're using calculators. We're not going to get the exact value, we're just going to get a really good idea for our sketch. So if you were going to sketch, there's no way you'd have this much accuracy, so you might actually just round it to -0.26 or even -0.3, but I'm not going to be that loose. I'm going to go ahead and keep a lot of stuff here. So again, it comes down to what you're trying to do as to how many decimals you keep. So that's the vertical asymptote, and there was only one of them. Now, how do we find horizontal asymptotes? For that, if you remember, a horizontal asymptote is defined very simply. As x approaches, and you need to check both positive infinity and negative infinity, because your graph may approach two different things. You could have a graph such as a logistic function, where you have two different horizontal asymptotes. So how we can do this in the calculator is actually quite simple, but it's going to use a different technique. So I'm going to go ahead and put my entire function back in. So we have to type it in. I'm going to go ahead and pause the video as I type this in, if the computer will let me. There we go. Okay, so now that we have our entire graph in, if I go ahead and go back to a zoom standard, you'll see this just verify that the graph looks the same, still looks how it did. And I have a good guess that my graph has a horizontal asymptote going towards 0 because my graph seems to disappear into the axes. But how I can verify this is actually kind of logical. I can use my table, so I'm going to go second table set, and I'm going to change my table to ask instead of auto. So this way, when I go ahead and look at the table, I can type in any number I want. So now I can't type in infinity, but I can type in a large number. So if I go ahead and type in a very large number, my calculator will tell me what the function is evaluated at that number. So you'll see this is 3e to the negative 18. What is your calculator saying when it says 3e negative 18? Well, that's its secret way of using scientific notation, saying it's to the negative 10 times 10 to the negative 18th. So I have to shift my decimal place over a whole bunch of spots. So then you can verify by doing even more, and you'll see it's that same number. It's just our e's keep getting bigger and bigger and bigger and bigger, which means we're shifting over more and more decimal places. So we have essentially 0.00000000, I'm not going to write all the zeros, 3, which is essentially saying as x approaches positive infinity, because I typed in really big numbers, as x approaches positive infinity, my graph is going towards 0. We can do the exact same logic for the negatives, where we just type in a very large negative number, and you will verify, yes, we have the same thing going on the other side. So therefore, I have a horizontal asymptote of y equaling 0. Now, you might be saying to yourself, what would that look like if it wasn't equaling 0? So very quickly, I'm just going to alter this equation just so we can talk about it. So instead of this being x squared, I'm going to make this x cubed. So therefore, my new function right up here would just have a cubed. So now if you go ahead and look at the graph of that, we should no longer, well, you can see actually, it still looks as if my graph is approaching 0 because it's hidden in the axis. But when I look at my table, you'll notice I'm not getting a 0 value here. I'm getting a specific value. I'm getting 0.025. And if you remember how you find horizontal asymptotes by hand, well, that just means you use the logic, at least how I like to teach it, is using the logic of as we approach infinity, what's happening to all these other numbers. And well, what's happening is the -1 doesn't matter, the x and the 1 don't matter, because they are so inconsequential. Oops, excuse me, this was cubed. They are so inconsequential in comparison to the size of x cubed that we don't really have to worry about them. So as x approaches infinity, what's going on here? We're left with y equals x cubed over 40x cubed. So that would simplify down to be 1 over 40. And interestingly enough, 1 over 40 happens to be that decimal we were seeing in the table. So you could see for this graph now, we could use the same method. So even though it looks as if our graph is approaching 0, when we go ahead and substitute in very large numbers, the calculator will let us know whether it's actually approaching 0 or whether it's actually approaching a value that we have hidden inside, hidden on that axis that you would never see. Another thing you can do is that little technique I was showing you of making your window, your y values, very small, so it kind of narrows your focus a little bit. And let's see if we'd actually be able to see it. We may not, because it may be too close still. Oh, there you go. So you can see once we made our y values much smaller, you can now clearly see as we approach infinity, and this is only 10, -10 and +10, but still, as you can see, we're not on that axis anymore. We are now above that axis. So I hope that logic helps. So to kind of recap, vertical asymptotes, take your denominator, set it equal to 0, or sorry, take your denominator, put it in the y1 line, and then look for where it equals 0 by calculating. Horizontal asymptotes, put your entire function in the calculator and use your table to evaluate values, and you can narrow your y values on your graph to make sure your teacher isn't hiding that there actually is a horizontal asymptote and you just can't see it because it was blending in with the axes. Okay, I hope that helps.